11.4 Tree diagrams. Counting principle. If a first experiment can be performed in m distinct ways and a second experiment can be formed in distinct ways, then the two experiments in this specific order can be performed in m times n distinct ways. Sample space. A list of all possible outcomes of an experiment. Sample point. Each individual outcome in a sample space. Tree diagrams are helpful in determining sample spaces. So we're actually going to be using tree diagrams to determine probability. Selecting ticket winners. You might remember tree diagrams from like pre-algebra or like anywhere from 5th to 9th grade. You might remember tree diagrams. So Insomniac has 2 tickets to give away to EDC Orlando. It held a contest and narrowed down the possible recipients down to 4 people: Aspen, Noah, Longinus, and Phyllis. The names of these 4 people will be selected at random from a hat, and the 2 people selected will be awarded the tickets. We're going to use the counting principle to determine the number of points in the sample space, construct a tree diagram, list the sample space, determine the probability that Aspen is selected, and determine the probability that Aspen is selected, then Longinus is selected. That's supposed to be Longinus. Alright, so let's do our counting principle. Part A. So counting principle, it stands for m times n. So we're picking 2 out of the 4 contestants. So 2 out of the 4 are going to win. So this is our first pick, and this is our second pick. Our first pick, there's 4 to pick from, and then we pick a winner. So we pick a winner, now there's only 3 left. So our sample space is 12. That means we only have 12 possible outcomes of winners. Let's actually draw that to see what a tree diagram looks to describe 12 possible winners. So we're picking 2 people to win. This is our first pick, and this is our second pick, and this is our sample space. So our first pick, Aspen can win, Noah can win, Longinus can win, and Phyllis can win. Then our second pick, if Aspen wins, only, because Aspen's out now, they already won. So that means Noah can win, Longinus can win, or Phyllis can win. If Noah's picked, then Aspen is left, Longinus is left, and Phyllis is left. If Longinus is picked, then you can pick Aspen, you can pick Noah, or you can pick Phyllis. If Phyllis is picked, then Aspen can be picked, Longinus can be picked, or Noah can be picked. I know I did that out of order, but that's okay. So these are all our possible outcomes. So we have AN, AL, AP, meaning Aspen and Noah can be the winners, Aspen and Longinus can be the winners, or Aspen and Phyllis can be the winner. If Noah is picked, it could be Noah Aspen, Noah Longinus, Noah Phyllis. If Longinus is picked, it can be Longinus Aspen, Longinus Noah, Longinus Phyllis. If Phyllis is picked, it could be Philip Aspen, Philip Longinus, or Philip Noah. Philip Phyllis. Phyllis, sorry. So this is our tree diagram and sample space. These are all of our possible outcomes. So you see how we have 12 in the sample space? That helps us answer a lot of questions. Determine the probability that Aspen is selected. So we're going to look for everywhere Aspen wins. So here, 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 here. So total, our sample space is 12. Aspen is picked 1, 2, 3, 4, 5, 6 times. So the probability of Aspen is 6 out of 12, which is 1/2. But doesn't that make sense if there's 4 people and they're picking two names, you have half of a chance, half of a probability. So the probability of Aspen being picked is half. They have a 50% chance of getting picked as a winner. Determine the probability that Aspen is selected, then Longinus is selected. So what we're looking for first is Aspen, then Longinus. So let's look for Aspen first, and then Longinus. So Aspen Longinus, I'm going to circle it in yellow, is right here. There's no other Aspen then Longinus. There's only one A then L. So the probability of Aspen then Longinus is only 1 out of the total 12. So if these two were friends and they wanted to go together, there's only a 1 out of 12 chance that they'll actually both be the winner. Selecting balls with replacement. 2 balls are to be selected with replacement from a bag that contains 1 red, 1 blue, 1 green, and 1 orange ball. We're going to use the counting principle to determine the number of points in the sample space, construct a true diagram, and list the sample space, and then we're going to do some probability stuff. Alrighty, part A I'm going to do over here to the right. We're going to use the counting principle to determine the number of points in the sample space. So we're picking 2 balls with replacement. With replacement. So remember, that means we pick one, we put it back. In the previous example, if you pick a winner, the winner doesn't go back into the pool to be drawn again. The winner already won. So that's why it's going to be a little different here with replacement. So we're picking 2 balls. This is our first pick and our second pick. Our first pick, we have 4 to pick from because we have a total of 4 balls, 1 red, 1 blue, 1 green, 1 orange. And then we put it back and still have 4 to pick from, so we have a total of 16 sample space. So we have 16 scenarios. Let's construct a tree diagram and list the sample space. So we're picking twice. We have 1 of each color. We have 1 red. We have 1 blue. We have 1 green. And we have 1 orange. So if I pick a red, if we pick red, remember we're doing with replacement. So if I pick the red, it goes back in the bag. I can pick it again. So I have every possibility of picking. If I pick a marble or if I pick a ball and I'm putting it back with replacement, I have the opportunity to pick every single ball again. So our second pick, it could either be red, blue, green, or orange. If I pick a blue, tally it, and then put it back, I can still pick red, blue, green, or orange. If we pick green, and put it back, we still have the opportunity to do red, blue, green, orange. And if we pick orange, we still have the opportunity to do red, blue, green, orange. So our sample space is red, 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 blue, red, green, red, orange. Then we have blue, red, blue, 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 green, blue, orange. Then we have green, red, green, blue, green, 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 orange. Then we have orange, red, orange, blue, orange, green, and orange, orange. So those are all of our possibilities, and we have 16 possibilities in our sample space. Determine the probability that the red ball is selected twice. So we're looking for red, red. So let's scour our sample space and look for double R. But we only have 1 double R. So we only have 1 out of 16 to get red, red. Determine the probability that neither ball selected is orange. So we want to look for everything that has no orange. So not orange. So anything that is not O. And remember, we have 16 possibilities. So anything without an O. That doesn't, that doesn't, that doesn't. This one, this one, this one. That one, that one, that one. That's it. So I have 9 that are not orange. So 9 out of 16 cannot be orange. All right. Now let's determine the probability that orange ball is selected at least once. So we want to know at least one orange. So from here, we want to look for everything that has an orange in it. This is where I suggest you pause it and try it. So out of our 16, we have, let's see how many have just orange. So this one, this one, this one, this one, this one, this one, and this one. So everything with an O, we have 1, 2, 3, 4, 5, 6, 7. 7 out of 16 have an orange in it. Probability of an event happening at least once. The probability of an event happening at least once is 1 minus the probability the event does not happen. For example, if you are planting flowers, suppose that the probability of not getting any red flowers from the seeds planted is 2 over 7. Then the probability of at least one red is 1 minus 2 over 7 is 5 over 7.